Welcome to KPIs and Simple Complex Systems with your hosts, James, Brian, and Will. In this exciting installment to ISYE 3104, we will be diving into some pretty interesting introductory topics that you need to learn early on. Don't forget rule number 4, don't get behind. The KPIs we will be focusing on in this lesson are utilization, throughput, and capacity. It's best to memorize these formulas as soon as possible, as they are critical to your basic understanding of this class. Utilization is the arrival rate of jobs over the effective processing rate of jobs. The throughput for a particular line is the bottleneck rate. The effective capacity of the system, in our examples, is determined by the station with the highest long-term utilization. In our upcoming examples, we will also focus on two important system dynamic concepts. First is deterministic arrival times. Deterministic arrival times mean that a new part to be worked on in our factory is delivered at an exact interval of time. In other words, if you were working on building widgets, all the pieces to build the widget arrive at our manufacturing system at an exact time. This makes our process have zero flow variability into the system. The other major system dynamic we will deal with is a system with unbalanced workstations. These systems have an unequal number of machines running in parallel at each workstation, as well as each workstation having the potential for different processing times. You will see in some examples that these dynamics add some more difficulty to our system than you see in PennyFab 1. In our first example, we start out with a 3-workstation system, and each workstation has one machine with a processing rate of 15 an hour, 20 an hour, and 18 an hour. You could also see this as an average processing time of 4 minutes, 3 minutes, and 3 1/3 minutes. It has a deterministic arrival rate, so a new job arrives to the system at a rate of 10 an hour, or 1 every 6 minutes. Now it is time to find the utilization, throughput, and capacity of our system. So looking at our first system, the main thing you have to realize is that we need to break the system into separate parts based on their workstations. You need to look at the system and realize that the initial arrival rate to the system, or 10 an hour, is an input to the first workstation, and we will use that to solve for the utilization and the throughput of the first station, or station 1. By doing this, we can once again determine the throughput and then treat this as the arrival rate for the next station. Once we have the arrival rate for the next station, we can find the utilization of station 2. With the utilization of station 2, we can figure out the throughput and the departure rate to station 3. And then lastly, we can solve for station 3, its throughput, and its utilization. So when we first look at station 1, the first step is calculating the utilization for the workstation. So as we saw in the example, the arrival rate is 10 per hour, the processing time is 15 per hour, and our utilization is just the arrival rate over the process rate. So I'll give you a couple of moments to solve this problem on your own, and then we'll move over to the next slide. So if you got a utilization of 0.667, you would be correct. Once again, the way to solve this is just the arrival rate over the process rate, so that's 10 parts per hour divided by 15 parts per hour, which gives us a value of 0.667 for utilization. If you didn't solve this correctly the first time, then go back and write it and solve it on your own, because we're going to have to do this for the rest of the workstations. The next thing that we have to solve for each individual station is the throughput. So first, think about what would happen to the throughput of the system once it hits that first station. And I'll wait a couple moments while you can think about what would happen. So if your intuition told you that the departure rate or the throughput through the station was going to remain the same as the arrival rate, you are correct. This is because if you think about this intuitively, there's 10 parts per hour coming into station 1, and station 1 can process 15 parts per hour. So the most amount of products that are going to go through station 1 per hour are 10 products per hour, because station 1 can handle the 10 products per hour that are coming into the workstation. So moving forward from station 1, we now need to solve for station 2 and station 3, both their utilization and their throughputs, so we can figure out what the capacity of the system will be at the very end. So I'll pause for a moment so you can start to solve for the utilization and throughputs of station 2 and station 3 on your own. So welcome back. So here are the answers to our first system example here. For station 2, you can see that the utilization is 0.5, and you can look at, for station 2, you can see that our processing rate was 20 an hour, and the arrival rate from station 1 was 10 an hour, so our utilization is 10 over 20, or 0.5. Because our station 2 can process 20 parts per hour, and only 10 arrive per hour, we know that all 10 that arrive are going to be processed in that hour. So there's 10 an hour that are going to move to station 3. Then for station 3, the arrival rate to station 3 is 10 parts per hour over a processing rate of 18 per hour, which means that our utilization will be 0.5556. And because there's 18 an hour processed at station 3 and only 10 an hour arrive, we know that all 10 are going to be processed in 1 hour. So here is a good point to once again pause the video if you got any answers wrong here, and to check and see how you did from your answers compared to the correct answers for this system. So now, after you've checked your utilization and arrival rates for this system, so lastly for the system, we need to figure out what is the overall system capacity. Capacity for a system is the throughput of the bottleneck of the system divided by the utilization of the bottleneck. The bottleneck of the system is the station with the highest long-term utilization. The long-term part is important because we want to look at our system in a steady state position. So not just at the very beginning of when you start releasing jobs into the system, but we want to know if at the long term, after we've released 100,000 parts into our system, which station has potential to get backed up the most. So, which station has the highest long-term utilization? So we see when we look at our system, the highest long-term utilization in our system will be station 1. Its utilization is 0.667 because the processing rate was 15 an hour and the arrival rate to station 1 was 10 per hour. So since we had already calculated the throughput of the station, because it was just the departure rate of station 1, we know that that is 10 parts per hour. So dividing 10 parts per hour by our utilization of 0.667, we get a value of 15 parts per hour as the capacity of our entire system. If you know this as a whole, this capacity is the total number of jobs that a system can turn into throughput. It determines the maximum level of throughput the system can handle. So if you remember back to the processing rates of our simple system, we had 15 parts per hour, 20 parts per hour, and 18 parts per hour. So when you think about how many parts per hour our system can handle, the minimum number of parts our system can handle, the most amount of parts the system can handle is 15 per hour. Because if we have more than 15 per hour, then our arrival rate to station 1 will be greater than the processing rate at station 1, which means we will have an exploding queue or a line that will continue to just get longer and longer because station 1 would not be able to cover the rate of jobs that would be flowing into it.
All right, everybody, we will now move on to a more challenging problem. So if you didn't completely understand the simple system, pause the video here and review your work. Otherwise, we could get started with the complex system dynamics. As you can see here, the first two system dynamics, deterministic arrival times and unbalanced work systems, are the same as the last simple problem. However, we are adding two new ones, a split routing component and a rework component. Both of these will cause a change in the arrival rates to the new workstations. Let's go ahead and review the system itself. As you can see, it has an arrival rate of 8 units per hour, and then it goes to station 1, where it has a processing rate of 12 units per hour. From there, there's a split routing, where 75% of the products will go to station 2, and 25% of the products will go to station 3. At station 2, they are processed at a rate of 15 units per hour. However, there is a rework component where 50% of the units that exit Station 2 go back into the arrivals for Station 2. For Station 3, units are processed at 6 units per hour. Finally, all those units go towards Station 4 and are processed at 9 units per hour. From here, all the units leave the system. Now let's go ahead and get started on solving the utilization and throughput. Now, go ahead and take a second to solve the utilization and throughput of Station 1. If you got a utilization of 0.75 and a throughput of 8 units per hour, you're on the right track. But now let's take a look at this split routing process. We'll take the throughput, 8 units per hour, and multiply it by the percentage of products that go to each of the next 2 stations. For Station 2, we'll multiply 0.75 times 8 units per hour and get an arrival rate of 6 units per hour. And then at Station 3, we'll multiply 0.25 times 8 units per hour and get an arrival rate of 2 units per hour. Now, at Station 2, things get even more challenging with the rework component, but we will still start by solving for utilization first. Looking at the arrivals, we have an arrival rate of 6 units per hour at Station 2. But we also have arrivals from rework, which is calculated at 50% of the departure rate. By adding these together, we get a total arrival rate of 9 units per hour. We can now solve the utilization as before, coming up with a solution of 0.6. And for throughput, it is also the same as last time, by looking at the station in the long run, where the total throughput will be 6 units per hour. Moving to Station 3, we have the 2 unit per hour arrival rate calculation from the split routing, and I have a 6 unit per hour processing rate. Take a moment here to solve the utilization and throughput of the system. If you got 0.33 for utilization and a throughput of 2 units per hour, you're on the right track. Finally, for Station 4, in order to calculate the utilization and throughput, we must start with the arrival rate, simply calculated by adding the arrivals together from both Station 2 and Station 3. We'll get an arrival rate of 8 units per hour. From here, it's just simple utilization and throughput calculations as done before. Take a moment to do both of these. Again, we have a utilization of 0.889 and a throughput of 8 units per hour. Now, let's move on to the larger picture. Well, James will teach you how to do the capacity of the complex system.
Hey everybody, James here, and I will be explaining the capacity for the complex system. Will helped us figure out the utilizations for each station and the throughput of the system. So let's move on from there. In order to find system capacity, we must first determine the station with the highest utilization. This is important because the station with the highest utilization is our bottleneck, and we need to know the bottleneck rate to find our system capacity. As you can see, the bottleneck is at Station 4 with the highest utilization at a whopping 0.889. Therefore, the bottleneck rate, RB, is 8 units per hour. Now that we know the bottleneck rate and utilization, we can do simple division to determine the system capacity. And there you have it. Our system's capacity is approximately 9 units per hour. In this video, you have learned about what utilization, throughput, and capacity mean in regards to manufacturing systems and how using information about inter-arrival times and station processing times allow us to calculate throughput and capacity for an entire system. Thanks for joining Brian, Will, and I for this video. I hope it was clear and concise enough to help you gain a deeper understanding of important key performance indicators for both simple and complex systems. Now who was that? You can't sneeze in here. Get your life together.